Hi, this is SM and welcome back to our channel Concept of Mechanical Engineering. In the previous class, we have already completed the work transfer theoretical part. Now we are going to see the numerical part of work transfer. Before we move on to the topic, let us see one topic, which is representation of various processes on TS diagram. Representation of various processes on TS diagram. This is our TS plot, where T is the temperature and S is the entropy. We will see the detail about the entropy in the entropy chapter. We are just looking the processes on TS diagram. So we have the general equation, this one, PV to power n equals to constant. So if we put n equals to gamma here, we will get PV to power gamma equals to constant, which is an isentropic process. So means entropy constant. Isentropic means entropy constant. So we will have a straight line here. This is our n equals to gamma. Now if we put PV to power here in this equation, if we put n equals to 1, let's put n equals to 1, we get PV equals to constant. This implies this is isothermal process. We have already seen in previous class isothermal process. This implies T equals to constant. T equals to constant means we will have a straight line parallel to the S axis, this one. This line represents isothermal process n equals to 1. Now we have already seen that for practical purpose, at value of n for polytropic process lies between 1 and gamma. So its graph will also be between 1 and gamma. So this is polytropic. N is between 1 and gamma. Now if we put n equals to infinity, so if we put n equals to infinity, we will get V equals to constant. We have already seen in previous class. So this is the graph for V equals to constant. And if we put n equals to 0, this implies we will get P equals to constant. That means isobaric process. Isobaric process. But the slope of isobaric process is less than compared to the slope of isochoric, that is constant volume process. So this is the graph for n equals to 0, that is isobaric process. N equals to infinity, this implies V equals to constant. N equals to 0, this implies P equals to constant. N equals to 1, this implies T equals to constant. N equals to gamma, this implies PV to power gamma equals to constant. Now this is the graph, the graphical representation of various processes on TS diagram. This is helpful to solve the questions which are asked in ESE examinations. V equals to constant, this means isochoric process. Now see this question. A system undergoes 3 processes as shown in the figure. Process 1 to 2 isobaric, process 2 to 3 adiabatic, gamma equals to 1.4, and process 3 to 1 isothermal. So we have given a 3 process. This is a diagram for the question. It is already given in the question. So process 1 to 2, we have isobaric process, that is pressure equals to constant. Process 2 to 3, it is adiabatic, that is PV to power gamma equals to constant. And process 3 to 1, this is isothermal, so T equals to constant, temperature equals to constant. Now we have to find out the value of V2 and net work done. So we know that for process 3 to 1, process 3 to 1, this is isothermal process. That means temperature constant. So we have PV equals to constant. This implies P1 V1 equals to P3 V3. We have given the value of pressure as 400 kilopascal. P1 and P2 equal because it is isobaric process, and the value of P3, that is pressure at point 3, is 100 kilopascal. So by putting, we get the value P1 400 into V1. V1 we have given 1 meter cube. 1 is equal to P3 100. V3 we have to find. So we get the value as V3 as, we cut 0, 4 meter cube. So the value of V3 is 4 meter cube. Now for process 2 to 3, process 2 to 3, this is adiabatic process. That means PV to power gamma equals to constant. This implies P2 V2 to power gamma is equal to P3 V3 to power gamma. From here we get the value as P2 V2 to power gamma is equal to P3 V3 to the power gamma. The value of P2 is 400 kilopascal. 400 into V2, we have to find gamma is 1.4 is equal to P3. P3 we have 100 into V3. We have already calculated, it is 4 meter cube. 4 into 1.4. This implies 100 will get cancelled out. So V2 to power 1.4 is equal to 4 to power 1.4 by 4 is equal to 4 to power 1.4 minus 1, because this is in by form. If we will put it up, it will subtract from the power. So it is 4 to power 4 to the power 0.4. This implies V2 is equal to 4 to the power 1.4 by 0.4, sorry, 0.4, 4 to the power 0.4 by 1.4. V2 is equal to 4 to the power 0.4 by 1.4. On solving, we get the value of V2 as 1.486 meter cube. So the value of V2 we have calculated this as 1.486. Now the net work done. So we know that net work done is equal to W net is equal to W for process 1 to 2 plus W for process 2 to 3 plus W for process 3 to 1. The summation of all these processes, we will get the net work done. So W1 to 2 plus W2 to 3 plus W3 to 1. Now W1 to 2. We know 1 to 2 is an isobaric process. So the work done is given as pressure is constant. So it will get out of the integration and we get the value as PV2 minus V1. Pressure we have 400 kilopascal. So it is 400 kilopascal into V2. We have already calculated it as 1.486 minus V1. It is given as 1. So it is 1. So on solving, we get the value as 194.4. 194.4. 194.4. And the unit is kilojoule because we have taken pressure in kilopascal. So the unit will is kilojoule. Now process 2 to 3. 2 to 3 is an adiabatic process. and the work done is given as P2 V2 to power gamma minus P3 V3 to the power gamma by gamma minus 1. So putting this value, we will get P2, we have already given, it is 400, into V2 we have calculated it as 1.486 to the power, let's put here P2, it is 400 into V2, 1.486 to the power gamma, that is 1.4, minus P3 we have 100 into V3 we have calculated V3 as 4 to the power 1.4 by 1.4. On solving we will get the value this as 486 kilojoule. 486 kilojoule, and this is positive. This also, sorry, not this one, this is also positive, that is work done for the process 1 to 2, we have got the positive value as 194.4, and the work done by the process 2 to 3 we have got the positive value as plus 486 kilojoule. Now we will find the work done by the process 3 to 1. So process 3 to 1, this is isothermal process, isothermal, this is isothermal process. So the work done is given by process 3 to 1 isothermal process, it is given as P3 V3 ln V1 by V3. This is P3, so we have the value of 100 kilopascal, 100 into V3 4 ln V1, it is 1 by V3, it is 4, sorry, V3 was, this was V3, so its value was 4. So 100 into, this is 400 ln 1 by 4. ln by 1 by 4 means ln 4 to the power minus 1. This means 400 into minus ln 4, because we know that ln x to the power minus 1 is equal to minus ln x. So this is minus ln 4. After calculation we will get the value as minus 554.52. This is the work done by the process 3 to 1, and it is negative. So the net work done, we have to calculate the net work done. The net work done is W net is equal to W by process 1 to 2 plus W by process 2 to 3 plus W by process 3 to 1. By the work done by the process 1 to 2 we have the value as plus 194.4 plus for the process 2 to 3 we have the value as 486, and for the process 3 to 1 we have minus 554.52, minus 554.52. On solving we get the value as 125.88. This is positive value, that we have got the net work done as positive. So we have already calculated this one V2, and we have also calculated this one net work done. Now we will see some conclusion. Now let us draw some conclusion from the question. This is the cycle we have on PV diagram this is process 1 to 2 and 2 to 3, 1 to 2, 2 to 3 and 3 to 1. 1 to 2 isobaric process, 2 to 3 adiabatic and 3 to 1 isothermal. So the area under the curve is the work done on PV diagram. So the area under the curve by the process 1 to 2 on PV diagram is the work done by the process 1 to 2. This area is the area and is the work done by the process 1 to 2. So this area is the work done by the process 1 to 2. So this is positive area or clockwise area. Now the area under the curve, this one, the area under the curve for the process 2 to 3, this area is the work done by the process 2 to 3. So this is the work done by the process 2 to 3. So this area is also positive area or clockwise area. But the area under the process 3 to 1 is the negative area, and this is anti-clockwise cycle. So 1 to 2 was clockwise cycle, 2 to 3 clockwise cycle, and this 3 to 1 is anti-clockwise cycle. Anti-clockwise cycle. So the area, this is the area under the process 3 to 1. This area, and this area is the negative area or anti-clockwise cycle. So clockwise cycle, sorry, anti-clockwise area. So positive area or clockwise area is the area under the process 1 to 2, and 2 to 3 is the positive area or clockwise area, but for process 3 to 1 it is anti-clockwise area or negative area. So this is clockwise area, this is clockwise area, and this is anti-clockwise area. So we have also, we can conclude one thing. So this is our PV diagram, and this is the process 1 to 3, 1 2 3. So the net work done by the cycle, see, the area under the curve 1 to 2 represents the work done by the process 1 to 2. The area under the curve 2 to 3 represents the work done by the process 2 to 3, and the area under the curve 3 to 1 represents the work done by the process 3 to 1. So this is positive area, we have got the value as in the question, and this is also positive area, and this area, the area under the curve 3 to 1 is the negative area. So if we subtract this area from the whole area, is subtract this area, the red one area, then we get the area under the curve, this one, the area under the cycle, this one. So this is the work done by the cycle. So this area represents the work done by the cycle. So W net, this is the net work done by the cycle, and this is positive. So expansion area, we have positive work, compression area we have negative work, now the conclusion. For PV diagram and closed system, Number 1, positive area or clockwise area? Positive area or clockwise area represents the work done by the system. That is positive work done. Positive work done. Positive work done. Negative area. Negative area or anti-clockwise area. Anti-clockwise area represents the work done by the work done on the system. Represents the work done on the system. That is negative work done. And the third one, work done by the cycle. So work done by the cycle, work done by the cycle is the area enclosed by the cycle on PV diagram. So the area enclosed by the cycle on PV diagram is the work done by the cycle. W net positive. So positive area represents the work done by the system. Negative area, that is the anti-clockwise area, represents the work done on the system, and the work done by the cycle is the area enclosed by the cycle on PV diagram, and this area is positive. Now the fourth conclusion is all clockwise cycle on PV diagram represents the power producing cycle. Represents the power producing cycle, that is net work done by cycle positive. And the fifth conclusion is all anti-clockwise cycle on PV diagram represents the power consuming cycle, that is net work done negative. So all clockwise cycle on PV diagram represents the power producing cycle, and all anti-clockwise cycle on PV diagram represents the power consuming cycle. See, this is a clockwise cycle here, so the net work done is positive. We have seen in the question we got the value as 125.88. So that was the positive work done by the cycle. So all clockwise cycle on PV diagram represents the power producing cycle, and all anti-clockwise cycle on PV diagram represents the power consuming cycle. Now let us see this question. An ideal gas is heated in a constant volume until its temperature is 3 times the original temperature. It is then expanded isothermally till it reaches its original pressure. The gas is then cooled at constant pressure until it restored the original state. Determine the net work done per kg of the gas. Take initial temperature at 350 Kelvin. Express your answer in terms of R gas constant. So let us solve this question. Let us first draw our PV diagram. This is our PV diagram. It is given in question an ideal gas. So ideal gas is given, is heated in a constant volume. So the process is constant volume. This is our constant volume. Process 1 to 2 is constant volume until its temperature is 3 times the original temperature, such that it is the temperature at T2 is 3 times the temperature at T1. So let us consider this point as P1, V1, T1, and this point as P2, V2, T2. It is then expanded isothermally till it reaches its original pressure. It is expanded isothermally, so such that it reaches at initial pressure. So this is our expansion, isothermal expansion, 2 to 3, such that the pressure at 3 is equal to the pressure at 1. The gas is then cooled at constant pressure until it restored the original state. Then after it is cooled such that it restores the original pressure. That is, it restores the original state. So the state, this. So from 1 to 2 it is heated in a constant volume, then it is expanded isothermally, T equals to constant, and then it is cooled back at constant pressure, that is isobaric. So this is isochoric constant volume process, this is isothermal process, and this is isobaric constant pressure process. Now we have to find that, determine the net work done per kg. So M is given, it is per kg, so M is 1 kg. So the value of M is 1, and the T1 is equal to 350 Kelvin. Express the answer in terms of R. R is a gas constant, so we have to get the answer in terms of R. Now we have to find out the net work done, W net. So W net is, we know that the work done by the cycle is the total work done by each process. So W net is equal to W122 plus W223 plus W321. Now work done by process 1 to 2. This process is an isochoric process, that is constant volume process. So we know that the work done by a constant volume process is 0, since V is equal to constant, dV is 0, so the work done is 0. Work done is 0. So the work done by an isochoric process, that is 1 to 2, is equal to 0. And since it is a constant volume process, so P is directly proportional to temperature. We can write P1 by P2, P1 by P2 equal to T1 by T2, and it is given that in question T2 is equal to, this is equal to 3 times of T1, because its temperature is 3 times the original temperature. So that temperature at T2 is equal to 3 times the temperature of T1. So we can put here P1 by P2 is equal to T1 by 3 T1. T1 cancel out. So P2 is equal to 3 P1. So we got the value P2 as 3 P1. Now work done by the process 2 to 3. Process 2 to 3 is an isothermal process. Isothermal, that is temperature constant. So we have the formula for work done. Work done 2 to 3 is P3 V3 ln P initial by P final, or we can write here MRT. As it is isothermal, T is constant. So since it is isothermal, this P3 V3 T3, the process 2 to 3 is isothermal process. So the value of T3 is equal to value of T2, and we know that the value of T2 is equal to 3 times of T1. So we know that we have this T3 is equal to T2 is equal to 3 times of T1. So we can put here this MRT T3. So from here we will get W223 is equal to MR T3. We can put 3 times T1 into ln P initial. P initial is the P2, that is equal to 3 times of P1. So P initial P2 by P final P3. So this is, from here we get the value 2 to 3 as MR 3 T1 into ln P2 is equal to 3 P1. So 3 P1 by and P3. Since the process is then it is cooled at constant pressure. So the process is constant process 3 to 1. So this P3 is equal to P1. So we can put here P3 as P1. This P1 cancel out. So we have W223 is equal to 3mR T1 ln 3, and 3 into, we have to calculate the value per kg. So m equals to 1 into R. T1 is given as 350 Kelvin. So 350 Kelvin into ln 3. On solving we get the value as 1153.54. So plus 1153.54 R, because we have to find the work done in terms of R. So it is in terms of R, kilojoule per kg. Now the process 3 to 1 is an isobaric process. So process 3 to 1 is an isobaric process. That means P equals to constant. So the work done is given as 3 to 1. Work done 3 to 1 is equal to P into V final minus V initial, and we have V final as V1, P into V1 minus V initial V3. So work done by 3 to 1, P into V1 minus V3. If we put P inside, we get PV1 minus PV3. We know from ideal gas equation PV equals to MRT. So in place of PVV1 we can put MRT1 minus MRT3. If we take MR common, we get MRT1 minus T3, and we know the value of T3 is equal to T2, and T2 is equal to 3 times of T1. So MRT1 minus 3T1, MR minus 2T1, we know that T1 is given as 350 Kelvin and mass is per kg. So substituting the value 1 into R into minus 2 into 350, we get the value of work done by process 321 as minus 700 R kilojoule per kg. Now net work done is equal to work done by process 122 plus work done by process 223 plus work done by process 321. Work done by process 122 0 plus work done by process 223 1153.54 R plus work done by 321 minus 700 R. So the value is 453.54 R is the net work done kilojoule per kg. So this is the net work done by the cycle. Now let us see this question. An insulated vertical cylinder contains 0.1 kg of argon ideal gas with a frictionless non-conducting piston as shown in the figure. The mass of the piston is 5 kg and initially rests on the bottom of the cylinder. The cylinder is connected to a nitrogen tank at 100 bar to a pipeline fitted with a valve. The valve is opened and the nitrogen enters the cylinder. During this process, the piston is lifted to a height of 10 cm by nitrogen gas. The initial temperature and the pressure of the argon are 1 bar and 300 Kelvin and the final temperature of the argon is 320 Kelvin. Gas constant of argon is R, that is R of argon is 0.208 kilojoule per kg Kelvin and gamma of argon is 1.67. We have to find the work done by the argon and work done by the nitrogen. So let's see solution. This is the initial stage. The diagram is given. So this is the insulated cylinder and this is the valve which is preventing to enter the nitrogen into the argon. Now let us draw the final condition of the cylinder. This is our cylinder and it is insulated, and now the valve is open, and after opening the valve the piston moves up. This is the final position of the piston. Now the difference in height, this is the height. Actually the piston moved 10 centimeter. So and the final temperature is 320 Kelvin. So we have to find the work done by the argon. Work done by the argon for argon, since it is insulated, the process is reversible adiabatic. The process is reversible adiabatic, and so we can apply for work done for argon P1 V1 minus P2 V2 by gamma minus 1 mR T1 minus T2 by gamma minus 1 PV equals to mRT. So we have placed mRT and we have taken mR out, so we get mR into T1 minus T2, and we know the mass is 0.1 kg, so 0.1 into R, it is given 0.208 and T1 we have 300 Kelvin, T2 we have 320 Kelvin, gamma 1.67 minus 1. On solving we get the value as minus 0.6208 kilojoule. So work done by argon is minus 0.6208 kilojoule. since it is negative, so work is not done by the argon, work is done on the argon. So it is not work done by the argon, it is work done on the argon. And if we write this sentence, then we can put here plus 0.6208. Negative sign represents that the work is done on the argon. So work done on the argon is plus 0.6208 kilojoule. Now, second part, work done by the nitrogen. Work done by the nitrogen, Wn2. This work done is equal to work done by the nitrogen on argon, because the work was done on the argon, so that work was done by the nitrogen. So the work done by nitrogen is equal to the work done by nitrogen on argon plus work done by nitrogen on piston, because it also lifted the piston up. So the work is done by nitrogen on argon as well as the work is done by nitrogen on piston. So this work we have plus 0.6208 plus the work done by the nitrogen is mgh, where m is the mass of the piston. So plus 0.6208 plus the mass of the piston, the mass of the piston was 5 kg. So 5 into g is the gravity, acceleration due to gravity 9.81 into height, h is the height in centimeter. So if we convert it in meter, we will get 0.1, and if the value of this one is in kilojoule, so we also convert this in kilojoule. So we will divide this by 1000. Now it is kilojoule. Solving, we get the value as 0.6250 kilojoule. This is the work done by the nitrogen. Now let us see this question. A fluid contained in a horizontal cylinder fitted with a frictionless piston is continuously mixed by means of a stirrer. The cylinder diameter is 0.4 meter. During the stirring process, watching for 10 minutes, piston slowly moves out at a distance of 0.485 meter at a constant atmospheric pressure of 101.325 kilopascal. The net work done by the fluid is 2 kilojoule. The speed of the motor driving the stirrer is 840 rpm. Determine the power of the motor and also find out the torque in the motor shaft. So a fluid contained in a horizontal cylinder fitted with a frictionless piston is continuously mixed by means of a stirrer, that is a fan. So let's draw the diagram. This is a frictionless piston cylinder arrangement. This is our cylinder and this is frictionless piston, and this is the fluid. It is and this is the stirrer. This is connected to a motor. So a fluid contained in a horizontal cylinder. This is a horizontal cylinder fitted with a frictionless piston. This piston is frictionless, is continuously mixed by means of a stirrer. This is the stirrer. The cylinder diameter is 0.4 meter. The diameter of the cylinder is 0.4 meter. During the stirring process, watching for 10 minutes, piston slowly moves out a distance of 0.485. After 10 minutes, the piston slowly moves out a distance of 0.485 meter, that is this distance. Initially the piston was here, and after the steering for 10 minutes the piston moves out slowly at a distance of 0.485 meter at a constant atmospheric pressure. The pressure is constant, which is atmospheric pressure, whose value is 101.325 kilopascal. Now the net work done by the fluid is 2 kilojoule. The net work done by the fluid is 2 kilojoule. The speed of the motor driving the steerer is 840 rpm. Determine the power of the motor and also find out the torque in the motor shaft. Now see, work done by the fluid is equal to work done by the fluid on steerer plus work done by the fluid on the piston. The net work done by the fluid is the work done by the fluid on the steerer plus work done by the fluid on the piston. So the net work done is given as 2 kilojoule, and this is equal to the work done by the fluid on steerer plus work done by the fluid on the piston. That is, this is the displacement, so the work done is pdv, and this work done, this p, we have the pressure 101.325 into change in volume dv. See, this is the displacement and this is the diameter. We know that if this is a cross section area, then this cross section area multiplied by the displacement, this is the volume. So from here we can calculate the volume here. V is equal to pi by 4 d square into length. We have the value of pi 3.14 by 4 into d is 0.4 square into length, this 0.485. So we can put this value. We will get the value of this as 6.175, and we substitute this value here, 6.175. From here we will get the value of work done by the fluid on steerer is equal to minus 4.175 kilojoule. Now we get the volume this as V is equal to pi by 4 d square into L, pi 3.14 by 4 into d. This is the diameter, so 0.4 square into length, this 0.485. So substituting this here by 4 into 0.4 square into 0.485, we get the value 2 is equal to work done by the fluid on steerer plus this this we get the value as 6.175 kilojoule. Now the work done by the fluid on a stirrer. So work done by the fluid on a stirrer is equal to 2 minus 6.175 kilojoule. This is equal to minus 4.175 kilojoule. Work done by the fluid on a stirrer is negative, that is minus 4.175. That means work done by the fluid, it is written. So work is done on the fluid by the stirrer. So it is work done by the stirrer on the fluid, and this is 4.175 kilojoule. This is the work which is done by the motor, the shaft of the motor. So we have to find the power of the motor. So we have the motor work, this equals to 4.175. Now after 10 minutes, we have watched for 10 minutes, so power is equal to work done by time taken in second. So work done, we have 4.175 by 10 into 60. We have the value, this 6.95 watt. So power, we got the power as 6.95 watt. Now we have to find the torque. So we know P is equal to 2 pi nt by 60. So this P is equal to 2 pi nt by 60, where T is the torque. We have the power value as 6.95 equal to 2 into 3.14 into N. We have the RPM as 840 into torque we have to find by 60. On solving, we get the value of torque as 0.079 Newton meter. So therefore torque is equal to 0.079 Newton meter. The question is, an engine cylinder has a piston area of 0.12 meter square and contains a gas at a pressure of 1500 kilopascal. The gas expands according to a process which is represented by a straight line on PV diagram. The final pressure is 150 kilopascal, and calculate the work done by the gas if the stroke length is 0.3 meter. So we have given the initial pressure as 1500 kilopascal and the final pressure as 150 kilopascal, and the stroke length 0.3 meter. So let us consider a piston cylinder arrangement. This is our piston cylinder arrangement. Initially the piston is here, which is at a position as TDC or IDC, inner dead center, or TDC, top dead center. Slowly it moves here at any position theta, and finally it reaches to BDC, that is bottom dead center or outer dead center, ODC or BDC. If this is connected by a connecting rod, and through this crankshaft, this is the radius of the crank and this is connecting rod, This is the radius of the crank. Now this distance is the stroke length. So the distance from inner dead center to outer dead center is the stroke length. Now we can represent this on PV diagram. Initially we have the piston here where pressure is 1500 kilopascal, and it expands and reaches a position this 2 from state 1 state 2 where the pressure is 150 kilopascal. Now we have to find the work done by the gas if the stroke length is 0.3 meter. So LS is equal to 2R, and we have given LS here 0.3 meter. We know the work done by a process on PV diagram is the area under the curve on PV diagram. So this work done by the gas is equal to area. This is a trapezium, so area is 1/2 into sum of parallel sides into distance between them. So half into sum of parallel sides means this distance, this is this sum, these are parallel sides, these two sides are parallel sides. So the sum is 1500 plus 150, 1500 plus 150 by 2 into distance between. This distance is swept length. This distance is stroke volume. So we can write here Vs. This stroke volume is equal to pi by 4 into d square into swept stroke length, because this is the cross section area and this into stroke length is the volume. So here diameter it is given as 0.1, so 3.14 by 4 into 0.12 square into swept length 0.3. Substituting this here, we get half into 1500 plus 150 by 2 into 3.14 by 4 into 0.12 square into 0.3. Solving, we get the value as 29.7 kilojoule. So this is the work done by the gas if the stroke length is 0.3. So today I have completed the numerical part of the work transfer. In next class we will start heat transfer, that will be start heat, and we will see the heat transfer there. So if you like this video or if you find this video helpful to you, so please like, subscribe and share amongst your friends.